Let us explore one of computer science's most influential algorithms, Quicksort. Quicksort follows a powerful idea: divide, partition, conquer. It begins by selecting a pivot. Partitioning then rearranges the elements, moving smaller values to one side and larger ones to the other. Finally, it recursively repeats this process on each partition, transforming disorder into clean order. Let's take a quick overview of how Quicksort works. Consider a random sequence of numbers. Quicksort brings order through one repeated idea: partitioning. It begins by selecting a pivot, say, the last element. Partitioning then rearranges the elements, moving smaller values to one side and larger ones to the other. The pivot is now in its final sorted position, with all smaller elements to its left and all larger elements to its right. Conquer means repeating the exact same trick on each side, again and again, until nothing is left to split. And the chaos we started with settles into perfect order. Now let us learn how partitioning works. This partitioning method is known as the Lomuto partition scheme. It is a standard algorithm used in Quicksort to reorder an array around a designated pivot element. Quicksort's core operation is partitioning, and it consists of 3 steps. First, select a pivot element from the array. Second, partition the array so everything smaller than the pivot moves left and everything larger moves right. Third, lock the pivot. Because every number to its left is smaller, and every number to its right is larger, the pivot will never need to move again. It is now in its final sorted position. Quicksort performs this partition in place. Consider this array and the algorithm. In the Lomuto partition scheme, we always select the rightmost element as the pivot. We initialize p_index to the start of the array. It tracks the boundary of the less than or equal region. We begin scanning the array with our loop variable I. 7 is greater than the pivot 4. The condition is false, so we do nothing and let I advance. 2 is less than 4. The condition is true. We swap it with the element at p_index, then increment p_index. 1 is also less than 4. Condition is true. Swap it with the element at p_index, then increment p_index. 6, 8, and 5 are all greater than 4. We simply advance I. 3 is less than 4. Condition is true. Swap it with the element at p_index, then increment p_index. The loop finishes. We perform one final swap outside the loop, that is, we swap the element at p_index with the pivot. The pivot is now locked. Partition returns index 3 to the caller. Notice what partition does not do. It does not sort the left side, nor the right side. It merely builds a wall. Let us map exactly how the computer executes the recursion. Let's dive deep into the Quicksort algorithm. A recursive call pauses the current work, pushes its state onto the call stack, and dives deeper. We begin with Quicksort 0 to 7 on the full array. Partition executes and locks the pivot 4 into index 3. We now hit the first recursive call for the left side. Quicksort 0 to 2. Quicksort 0 to 2 is pushed on top of the stack, and we descend into it. Its partition locks 3 at index 2. It recurses left into Quicksort 0 to 1. Quicksort 0 to 1 is pushed on top, and we enter it. Partition swaps 2 and 1, locking 1 at index 0. The subarray becomes 1, 2. Now its left child. Quicksort 0 to -1. Quicksort 0 to -1 is pushed, but watch the base case. This is as deep as we go. The stack's height is the extra memory Quicksort needs, only about log n frames. Start is now greater than end, so the base case triggers, and it returns instantly and pops. Back inside 0 to 1, we call the right child. Quicksort 1 to 1. Quicksort 1 to 1 is pushed. A single element is already sorted, so 2 locks in place, and it returns. Quicksort 0 to 1 is finished. It pops off the stack. Back in 0 to 2, the left is done, so we call the right child. Quicksort 3 to 2. Quicksort 3 to 2 is pushed. This hits the base case immediately and returns. Quicksort 0 to 2 is fully resolved and pops off the stack. Back at the root, the entire left side is sorted. 1, 2, 3. Now the right side of the root. Quicksort 4 to 7. It is pushed, and the very same fractal of partitions plays out on the right. Partition after partition, each pivot snaps into place until the right half is sorted. 5, 6, 7, 8. Every call has returned. The stack is empty, and every element is locked in its final position. From a scramble of 8 numbers to perfect order, built entirely from one small idea. Partition, then recurse. Let us compare quicksort with mergesort. While mergesort guarantees n log n time, it requires auxiliary space. Quicksort achieves that same average speed while operating entirely in place. Why is quicksort considered one of the most practical sorting algorithms in modern computing? Let's look at its complexity. Quicksort's speed comes down to one thing: the shape of its recursion tree. When each pivot splits the array near the middle, the tree stays balanced and shallow, only about log n levels deep. Every level touches all n elements, so the total work is n log n. With our last element pivot rule, sorted input repeatedly chooses the largest element. Each call removes only one item, so the tree degenerates into a chain n levels deep. That is n squared. A common remedy is to choose the pivot randomly. Persistently one-sided partitions become unlikely, regardless of the input's original order. Random pivots give expected n log n time on any fixed input, although the theoretical worst case remains n squared. The final verdict for quicksort: expected time is n log n, though the worst case remains n squared. Space is practically in place, taking O log n for the call stack. However, it is an unstable sort. Quick recap. Quicksort sorts an array by repeatedly partitioning it around a pivot element. After each partition, the pivot is placed in its correct sorted position, and the same process is applied recursively to the subarrays on either side until the entire array is sorted. Thanks for watching.